selection and choose the right column for your task. So these are two questions I want you to bear in mind while you are reading through and while you are studying today's topic of overall instrumentation. And then we're going to start in 5 minutes.
Yeah.
I know what you're looking at. It's a video of the guy on top of the cell. That's the solution. Ban on road, ban on grass, ban on footpath. Okay, look.
Can I call you back? I'm actually in my lectures. Who's that? I don't know who that is. Who's insurance company? Who's insurance company? No, they know the Prudential is now.
They just like search in any kind of like, they hack the thing and then they find out the number, then they just call.
Yeah, so creepy. Like your info is out there.
Yeah.
Because the people who use TV, they like enlightened. They have seen the type.
Mira.
Alright, let's make a start.
10 hours later.
Wow.
Shut off all.
Teacher, we're watching movie.
Yeah, I'm watching movie. Wow, this is very cozy.
Alright,
It's so nice.
we talked about instrumentation. There are two major components you need to
Yes.
put it quite well.
No, it's I move it, that's why it dropped.
Right, injector, and then detector, and of course the column, right? And the column is, in another word, is essentially the heart of the instrument because the actual compound separation happens in the column. Right. So just now I was asking, and now can any one of you answer the question and what is the injector for in the GC?
To put in the gas. The solid or the liquid one to vaporize.
Okay, so now you recall the right way. Actually, a more scientific way is we have a task, right? We go to study some products. So actually, it's for you. The injector fundamentally is for you to introduce the sample, right? The product, maybe it is a Coca-Cola, maybe it is a Panadol tablet, right? So it's for you to introduce the sample into the instrument. But one of the key things you should remember, right? So injector actually is a device, right? Allow you to introduce the sample into the instrument in a reproducible manner. Right? But one thing I want you to pay attention to is in the previous lecture we actually discussed that the GC technique, right? It is a powerful technique, but obviously it cannot solve all problems. That means it's not applicable in every scenarios, right? So there's a limitation. So which compound, right? If you want to study certain compound, which compound is more suitable for this particular technique? This one we discussed. Can anyone of you still recall?
I can repeat.
Which compound is more suitable? Also, for the GC technique is more applicable in what kind of a scenario?
The thing is gaseous, right?
Right. You need to think about the nature of your so-called targets, the compounds you want to study. The condition is the compound you're going to study. They need to be volatile.
Oh.
Right? You need to be able to vaporize them. Then you can surely consider this technique. We do understand in reality there are many products, there are many chemicals, they are not that easy to be vaporized, right? Some chemicals with very high boiling point. So that's why in the first place, this technique, in principle, is not the best technique, it's not suitable. So that's why all this we need to bear in mind. So So when we come to designing an injector, so we also need to take this into consideration because the injector is on. Because in general we say if you're an engineer, you design the device. So of course the consideration is why you do it. The device can help you to do things automatically now, instead of just manually 100% do it by our hands, right? So the important thing is with the device, with the help of the device, you can do it. You can introduce a sample in a very reproducible manner. But this device will also need to help you to vaporize the sample. So that's why if you see the design of the injector, so there's a diagram of a simple detector. So actually, detector is just like a small container. Sorry, the injector is just like a small container. But outside, usually there's one layer of the jacket, right? Actually, it's a heater. So they design this way. Why we need a heater in the injector? Because when you put something inside, straight away, we would like to heat this compartment, also for the small component, heat it up, and all the way to a very, very high temperature. So then what will happen? So whenever we put it in, they will be vaporized straight away. Right. So then the mobile phase in the GC technique, gas converter, then the mobile phase comes in. So mobile phase can easily carry or bring those so-called products or so-called analytes into the instrument, into the column. So that is the design thinking. So that is the design behind all these components or instrument components. So if you understand this, then when you in the lab, when you handle the instrument, right, then other than scientific things, then the safety is also we need to pay attention to safety. So when you handle these components like injector all these, bear in mind, temperature is a potential safety hazard, but you need to be careful. Why is that so? Because the injector, right, I said we need to provide huge energy to vaporize things. The temperature can easily go up to 200 degrees Celsius, 300. If you imagine it's no protection, if your bare hand, you touch your finger, you touch the injector, you straight away get burned, right? So I sent you to okay, but luckily because this technique has been developed for many years, and all these safety measures are in place. That nowadays a modern GC instrument is actually quite used for operation. We have all the safety measures. All right, so that's why it's very straightforward. But the thing is, this technique was developed actually more than a few decades already. Actually, the original technique, the chromatography separation was discovered more than a century ago. Then the industrial instrumentation, with the advancement of the technology, and now we can have a fully automatic GC instruments. So originally, right, with the development, historically there was this kind of column, we call it pack column. Even during my college time, when I did the first GC experiment, right, in college, we need to prepare this column by ourselves. How to prepare? Actually, it's not very difficult. So we just get a tube, whether it's a glass tube or glass tube, right? And the tube is not very big. It's kind of in terms of diameter, it's somewhat similar to this or slightly smaller. I take the tube, and then I put in the packing material. It can be some fine particles with certain kind of chemical properties, or even those quartz groups. Not cotton, but in actual scientific experiment we don't use cotton. Cotton don't have the so-called properties can give you the reproduce one. So all this packing material you put it in and pack it nicely, and we actually can install a column, a GC column by itself, and carry out the separation. pressure, carry out experiment. But nowadays, all these are commercialized, and all the columns are fully developed in a very robust manner. But in terms of industry application, they still have this so-called PET column. Later on, we'll revisit this, why today there's still such a need. We still have to keep the PET column. But then, come to the modern application, most of the time we'll use another type of column, it's called capillary. Why is that so? Because for PET column, if you imagine a tube or a column inside with the packing material with this size, so you imagine you can easily introduce 1 ml of the sample inside, right? Just now we use a syringe. Today we still use syringe. This is one. I'm not sure about your lab schedule. Maybe this week or next week, you go to the lab, you'll be given this syringe. So for your experiment, you're going to handle the sample, do the sample treatment, and then introduce the sample by using the syringe manually. So it can be done automatically. So that means the instrument, they come with this injector, an auto injector, the syringe is also installed inside. It can take the sample automatically, do the injection automatically. But we would like you to hands-on one. So when you introduce the sample inside, you can easily introduce 1 ml. Can you now visualize how much is 1 ml of the sample? Is 1 ml a lot? No, not a lot. So with a syringe, with a medical syringe, can you manage to do that? Yes, no? The answer is, what happens if I ask you to reduce the sample size? You just need to introduce half a ml. Can you do that? Based on your experience, based on imagination, can you do that? Yes, right? Still yes, right? You take a smaller syringe, yes. There's a reason behind. Let's say the assumption is no choice, because for figure out the solution, I don't need 1 ml, I don't need half a ml. I only need 1% of 1 ml, 0.0 ml. Sorry, 0.01 ml. How can you do it? Can you do it? It's very difficult, right? So 0.01 ml is just tiny bit of the solution of the sample. How can you, with a syringe, it's very difficult. So that's why later on, based on our experiment results, then scientists will realize the PET column and then the injector, a single injector for you to directly introduce the sample directly into the column comes with a limitation. What happens if we just need a tiny bit of the sample into the instrument, into the column, right? Then how to do that? So that's why on one hand is we need to significantly reduce the size of the column and make it really, really tiny. Then this one is called capillary GC column. The time I talked to you, I mentioned to you the PET column. The tube size is just maybe half of this. And then how about the length?
So it could be
Maybe
30,
1
40
meter. But capillary column, in terms of diameter, is 100 times smaller than this. I show you an actual one, later you know. Then in terms of total length, 30 meter is a norm. But then, if that's the case, do we need a big room, 30 meter in length? We need a chemistry lab, 30 meter in length. And then house the instrument, because the column is 30 meter, do we need to do that? No need. Because the capillary column is so tiny, it's just like our hair, right? So you can roll it up. And then you just need a tiny space to house the capillary column. So that is what chemists develop. But the second thing is, if the column is so tiny, how can I introduce 0.01 ml of sample into the sample? So that's why they modified the original injector. The idea is, you can see the right hand side, there's a yellow color thing. So that is a special valve and so-called a special venting system. So on top, the syringe either is manual or the machine does for it automatically. You still introduce, let's say 1 ml. With this 1 ml, the 1 ml solution, usually we do certain kind of sample treatment. If the original product is a tablet, it's a solid, usually like your UV experiment, we need to do certain treatment and convert it into solution. A solution is the actual sample we introduce in the instrument through the injector. So this 1 ml solution, once go into the injector, the same thing will happen. So temperature heats up all the way to 300 degrees, everything vaporized. But what happened next is different. Original PET column vaporize, all these things, vapors go into the PET column together with mobile gas. But this capillary column, so the detector is called split detector, the split injector. So the device, with the advancement of the mechanical and electrical engineering, so you will be able to make the switch and just allow 1% of this 1 ml vapor goes into this very, very tiny column, capillary column. Then how about the remaining 99%? 1% go down, go into the capillary column. And 99%, the modern injector will be able to direct the remaining 99% to the vent, to the exhaust. So vent it out. So the instrument is actually just taking in 1% of 1 ml. So that's why this injector is called split injector. It's together with taking a capillary column. Is it okay? There is a strong reason why we just need to introduce such a tiny bit. So because of this requirement, so scientists, chemists, together with engineers, we devised this capillary column and split injector. So you can see this tiny tube, somewhat like just slightly bigger than our hand, right? It's called capillary column, and we roll it up, right? So the total length of this is the actual GC column, okay? So the total length is 30 meters in length, but it's just small. We just need a small space to house this column. So you pass around, everybody, you take a look. So later, go into the lab, we still have a chance to hands on. All right, that's our injector.
After the split band, so then after the split band, after the split band, it's just separated out.
Oh, you mean, yeah, that one go into environment. I understand. So all
cannot
this,
be like reused.
All this, no, not reused. All this has been taken into consideration. So the instrument is designed in a way, the exhaust, right, is not. So that's why when we go to scientific lab, safety is important. What happens if product is toxic? Right? So you vaporize it, 99% come to us, then it's very scary, don't worry. So all this has been taken into consideration. Linked to exhaust, so that's why the 3C instrument need to have a proper venting system. So all the way linked to the exhaust, linked to the so-called the fume hood, do the proper treatment and go into the environment. Right? So the split injector, right, the advantage is the amount of sample introduced in the column can be easily varied. So today I can do the programming, right? I can this experiment I can just introduce 1% of 1 ml into it. Next experiment I need 5%. So you can vary the amount of the sample to be introduced into the analysis very, very easily, right? So that's one of the advantage. Okay, so this is the injector. Then how about the column is the stationary phase? We'll come back to this very soon. Then another important component in the system is the mobile phase. So that's why we need, recall last week, we show you the schematic diagram. You need a gas supply system. But for GC, usually have you seen the industry, the gas cylinder before? The other thing is, yes, very similar thing is in a hawker center, the LPG tank, but the one is much bigger, right? So similarly, there's a small stainless steel, the gas cylinder. So the pressurize the gas inside. So they will provide the gas. But mobile phase, because the requirement, we usually use the chemical inert gas. So these are the few most commonly used gas. For instance, helium, nitrogen, so on and so forth. Most of the time we use nitrogen because the cost is still acceptable. Helium, likewise, because the industry, the efficient, the large scale production, the cost is also acceptable. But helium is a good, scientifically, chemically, is a good choice. But the only thing is, commercially, it's too expensive for our routine operation. Hydrogen is possible, can be used as a mobile phase, but hydrogen is a safety concern because we understand hydrogen is so-called
Oh my
hydrogen is a flammable item, so you need to handle with care, right?
Sure.
So
You said this kind of thing is 1 mil. So 1 mil of helium can't be that expensive, right?
no. You need to think about it. When you do an experiment, so experiment you carry out for 1 hour. 1 hour. The mobile phase,
you just like throw
you
your
need to
money
turn on,
like
you need
99%
to
just
provide, you need to supply the gas continuously non-stop
okay.
for 1 hour. So over time, the usage is high, right? So the material cost is relatively high.
So it's expensive but it's common.
Okay? So another
It's
requirement
expensive
is
but it's
this
common.
gas, this gas must be very pure
No, the helium.
and dry. So that's why we can give you a good
Yeah.
separation.
And to thank you.
English.
Okay, coming to the color.
Sorry.
So just now we mentioned there are 2 types of column, right? 2 types of column. So one is so-called pack column.
It's funny how
So pack column allows you to introduce large amount of samples. So in today's application, we still use pack column for certain kind of very special kind of application. Because if there's no choice, right? If you have to introduce a lot of samples, maybe for instance to increase the sensitivity this so on and so forth is a special reason. So you have to use a big pack column. Then the capillary column, right, is can give you the very high separation efficiency, and it saves you a lot of the product. So you don't need a lot of products. So also bring down your product analysis cost. Another thing is, next week, if we do our own experiment, then you will know the column, right? This column, we usually house it in a small compartment, we call it oven, right? So like the injector, we house it in the oven because we would like to do the temperature control. Because based on the separation principle, temperature has a direct effect on the separation. So this one will go into more detail in next week, right? So we can do the temperature programming to adjust the temperature and then help to improve the separation effect. So that's why together with column, we have this oven to house the GC column. Right, so with this, we quickly recall what is now we understand very well what is the function of the injector, right? And then, how could an analysis be affected by the quality of the GC column if the column has been deteriorated? Can you make a guess?
You won't get very good separation.
Okay, fair enough. That may happen. What else? Because we say column is the heart of the instrument, is where the actual separation happens. If this column damage,
No more separation.
sorry again?
No more separation.
No more separation, similar to his comment, right? What else?
Your machine doesn't work basically.
Okay, one of the things, this one again will elaborate again. Because the separation happens within the column, and then last time we talked about the GC result, and then the GC result we call it is a chromatogram, right? So we talk about retention time of a particular chemical. So if the column is aging, is deteriorating, then the retention time may shift. Then this resulting in a very serious and very critical consequences. Okay, I leave it with you first. You think about if retention time is shifting. Morning the retention time is 1.1 minutes. Then afternoon, the most extreme case, then afternoon we repeat the experiment, then retention time shift from 1.1 minute to 1.2 minutes for exactly the same product, same solution. Maybe it's the same solution you prepare in the morning, you don't even touch it, right? You don't even change it, right? So afternoon you repeat, 1.2 already. Then a day later, 1.3 already. So this is a serious issue, so we'll revisit this, but I will share with you, this may happen. Then even more serious problem is the column is damaged. It resulting in a very, very bad separation. This may happen. So in that case, the column no use already, right? All right. So we move on. The next few slides will explain to you different type of columns. So I leave it because we are self-directed learning. I leave it with you. You do your own reading and try to understand. Basically, what it tells you is the pack column. As I said just now, is the big tube. We just throw in the appropriate packing material to pack the column, and then the separation happens inside. Then the capital column. Now today there are two major different types. One is like in your house, in my house, in this LT, right? The concrete wall. So usually we paint a layer of chemical. This is called Nippon paint, right? So in the column, likewise, there's a special. We apply a special chemical, and usually it's a special solvent. Then we coated the inner surface. You imagine the column is already so tiny, but now with this the good engineering techniques, all this, will still be able to coat the inside, the internal surface with a very, very thin layer of liquid solvent, which is on your left. So one whole layer, homogeneously, a layer of organic solvent, that's called WCOT, coated with a special solvent. But another technique is, instead of one homogeneous layer of the liquid solvent, we can pack and we can stick onto the internal wall of the column with those very, very tiny particles. So the difference between these two is, this one is the homogeneity is a liquid, right? It's a liquid chemical. On the right hand side is a solid chemical. Let me ask you, what's the difference between these two different treatments? Exactly. The one on the right hand side, it further increase the overall surface areas of this particular chemical, right? So that again, that will result into a very direct effect. With high surface area, then the interaction becomes more, right? So it will directly impact and affect the separation efficiency. Okay? Right? But this one, you don't need to remember, you just need to try to understand. And these few slides I leave it with you. But more importantly, right, you don't need to remember the acronym, whether it's WCO, whatever, right? But more importantly is to understand the separation principle. So just now I asked the second question, right? I asked you to think about, okay, let's say commercially there are many different types of GC columns. How do we make a column selection? So that's why you need to go back to the separation principle. Think about how different compounds can be separated in the GC column. Then you make certain kind of decision. So first of all, we need to think about, again, back to GC separation. We are saying that in the first place, the chemicals you're going to study, they must have this property, also called the character. They need to be volatile in the first place, right? So they are volatile. So that's why in the injector, we'll be able to heat up the temperature and vaporize them. But if we do that, you can imagine the vapors. Is it above degrees Celsius or below? Of course, below lah, above lah, right? So very easily, it may be, in many cases, it may be even above 100 degrees Celsius, right? So if you choose, just how we say that the column is designed in this manner. If this particular chemical you use for your GC column, if it's not thermally stable, so when the mobile gas comes in, when the analytes comes in, when the chemicals comes in, it straight away damage the coating, right? So this is one of the very important consideration. So the other thing is based on the separation principle, because we know GC separation is fundamentally is between the interaction. Let's say now I'm the stationary phase. You are the so-called caffeine chemical. Right? You come in, then we have interaction. What's our interaction? Two major types. One is if we attract each other, I'm going to retain you. Safely retain you means now you travel. This one we discussed previously. Now you travel very slowly in a column. Another interactions, we have a very minimal interaction. You come in, then you go away. You come in and go away. How? Because mobile phase, right? Mobile phase is constantly flow through the column. So mobile phase will push you through the column. So two different types. So all this related to the chemical property of the stationary phase, the chemical we use, and then the chemical property of the molecule, let's say your caffeine or your Panadol, right? The